There is a particular kind of discomfort that comes from realizing the universe does not care about us. Not in a cruel way, not with any malice, but in the far more unsettling way of pure indifference. The cosmos operates according to laws that were written into its foundations long before life had any chance to take hold, and those laws will continue to execute with flawless precision long after the last living thing draws its final breath. That is not poetry, that is physics. We tend to think of life as the natural state of things. We look around and see a world teeming with organisms, from the bacteria thriving in volcanic vents at the bottom of the ocean to the birds migrating across entire hemispheres, guided by the magnetic field of this planet. Life seems so pervasive, so resilient, that it is easy to fall into the assumption that it is somehow protected, somehow central to the story the universe is telling. But the fossil record, that extraordinary archive pressed into rock over hundreds of millions of years, tells a very different story. It tells us that the vast majority of species that have ever existed on this planet are already gone. It tells us that life has come to the very edge of complete erasure multiple times. And it tells us, with a quiet and unavoidable certainty, that another such event is not a possibility. It is a mathematical certainty built into the structure of this solar system and the galaxy it travels through. To understand why, you have to step back from the scale of a human lifetime, even from the scale of human civilization, and think in geological time. 4.5 billion years is roughly how long this planet has existed. In that span, there have been at least 5 events so catastrophic that they restructured the entire web of life on Earth. Scientists call them mass extinctions, moments when the ordinary background rate of species loss accelerated so dramatically that entire ecosystems collapsed. The worst of these, the one at the boundary between the Permian and Triassic periods, roughly 250 million years ago, killed something close to 96% of all marine species and 70% of all terrestrial vertebrate species. Nearly everything alive on this planet at that moment ceased to exist. The planet was not destroyed. The atmosphere remained. The oceans remained. But the community of life that had taken hundreds of millions of years to assemble was essentially erased. What causes events of such magnitude? This is where physics enters the picture and where the cosmic scale of the problem becomes unavoidable. The mechanisms are several, and they are all rooted in processes that operate at scales far beyond anything we can influence or negotiate with. Consider first the most dramatic case, the one most people are familiar with, the impact of a large asteroid or comet. Our solar system formed from a disk of gas and dust approximately 4.5 billion years ago. Most of that material was swept up into the planets, moons, and other bodies we observe today. But vast reservoirs of rocky and icy debris remain. The asteroid belt between Mars and Jupiter contains millions of objects. The Kuiper belt beyond Neptune holds countless more. And farther still, extending to roughly a light year from the Sun, lies the Oort Cloud, a vast spherical shell of cometary bodies loosely bound by the Sun's gravity, estimated to contain trillions of objects. These reservoirs are not static. They are dynamic, perturbed by gravitational interactions with the giant planets, by the gravitational influence of passing stars, and by what astronomers call the galactic tide. This last effect is particularly worth dwelling on. Our solar system does not sit still in the Milky Way. It orbits the galactic center at roughly 800,000 kilometers per hour, completing one full orbit in approximately 230 million years. And as it travels, it bobs up and down through the plane of the galaxy like a ship cresting waves on a slow cosmic sea. Every time it passes through regions of higher stellar density near the galactic midplane, the gravitational perturbations on the Oort cloud intensify, sending showers of cometary debris inward toward the inner solar system. The mathematics here is not speculative. It is derived from the same gravitational physics that allows us to predict the orbits of planets with extraordinary precision. The galactic oscillation of our solar system has a period estimated at somewhere between 30 and 40 million years. And if you look at the geological record with fresh eyes, you notice something striking. There appears to be a rough periodicity to major impact events, spaced at intervals that echo this galactic rhythm. The numbers are not perfect, and the science is still actively discussed, but the underlying principle is clear. Our journey through the galaxy is not a smooth, uneventful ride. It is a passage through a dynamic gravitational environment that periodically stirs the debris left over from the formation of the solar system. The asteroid that struck the Yucatan Peninsula 66 million years ago, the one responsible for the extinction of the non-avian dinosaurs, was somewhere between 10 and 14 kilometers in diameter. When an object of that size enters the atmosphere, the energy released upon impact is roughly 10 billion times greater than the bomb that destroyed Hiroshima. The immediate fireball is only the beginning. Debris is thrown into the upper atmosphere. Soot from continent-spanning wildfires follows. Within weeks, sunlight is blocked on a global scale. Photosynthesis slows dramatically. Plants die. The food chains built upon them collapse. The temperature drops, and does so quickly enough that organisms cannot adapt. A nuclear winter created not by any human technology, but by pure geophysical mechanics, reshapes the biosphere in a matter of years. And here is what the physics tells us plainly. The inventory of near-Earth objects large enough to cause a mass extinction level event is not empty. The vast majority of objects in that size range have now been cataloged thanks to decades of dedicated sky surveys. But the cometary reservoir, the Oort Cloud, represents a population we cannot fully survey with current technology. Objects bound loosely to the Sun at distances so enormous that we cannot resolve them individually. The perturbation of that reservoir by stellar encounters and galactic tides is ongoing, unpredictable at long timescales, and fundamentally beyond any intervention we could currently conceive. But impacts are only one mechanism. The fossil record points to others, and they are no less humbling. Volcanic provinces known as large igneous provinces have been identified at several extinction boundaries. These are not ordinary volcanic eruptions. They are geological episodes during which enormous volumes of magma rise through the crust and pour across the surface over periods of tens of thousands to hundreds of thousands of years. The Deccan Traps in present-day India, for example, are the remnant of such an event, and they coincide in time with the same extinction that ended the dinosaurs, suggesting that multiple stresses were already straining the biosphere even before the asteroid delivered its final blow. When a large igneous province erupts over geological timescales, it releases staggering quantities of carbon dioxide and sulfur dioxide into the atmosphere. The sulfur compounds initially cool the planet by reflecting sunlight, but sulfur washes out of the atmosphere relatively quickly in acid rain. What remains is the carbon dioxide, accumulating in the atmosphere and the oceans over thousands of years, acidifying the seas and warming the climate. The combination of rapid climate shifts in both directions, ocean acidification, and the physical disruption of ecosystems can be sufficient to collapse the web of life even without an impact from space. What drives these volcanic episodes? The answer lies in the dynamics of the mantle, the semi-solid rock that makes up the vast bulk of this planet between its crust and its iron core. Heat flows from the interior outward, and it does so through convection, enormous slow currents of rock that move over millions of years. This convective system generates instabilities, localized upwellings of especially hot material called mantle plumes that can punch through the crust and produce precisely these large igneous provinces. The mantle is not a system we can manage. Its dynamics are governed by pressures and temperatures and timescales that dwarf anything on the surface. Then there is the slow evolution of the sun itself. Our sun, like all stars, is a nuclear engine. In its core, hydrogen nuclei fuse into helium, releasing energy that eventually radiates outward as light and heat. Over time, as hydrogen is consumed, the sun gradually brightens. Over the course of its lifetime, the sun has become roughly 30% more luminous than it was when the solar system formed. This brightening, while imperceptibly slow on human timescales, has profound consequences over geological time. Roughly 1 billion years from now, the sun will be bright enough that the oceans of Earth will begin a runaway evaporative process, and eventually the conditions necessary for liquid water on the surface will no longer exist. Long before that, the conditions that complex multicellular life depends on will be fundamentally altered. This is not catastrophism. This is stellar physics, the same physics that allows us to model the behavior of stars across the universe. The sun is middle-aged, burning through its hydrogen fuel on a schedule determined by its mass and the laws of nuclear physics. It has no mechanism for consultation, no way to adjust its output in response to the needs of the organisms living on the third planet in its system. So where does this leave us? We are, at this moment in the history of this planet, a species that has become aware of these mechanisms. We can model the orbits of near-Earth asteroids with precision sufficient to predict potential impacts decades in advance. We have begun to develop, in an early and tentative way, the capability to deflect small objects on collision courses with Earth. The DART mission, which successfully altered the orbit of an asteroid named Dimorphos in late 2022, demonstrated that the principle is sound. But deflecting a small asteroid that we have years to prepare for is a very different proposition from the full range of mechanisms we have been discussing. We cannot deflect a comet that enters the inner solar system from the Oort Cloud on a timescale of months. We cannot stop a large igneous province from erupting. We cannot slow the brightening of the sun. What we can do, and this is perhaps the most important thing physics teaches us about our situation, is understand the problem with extraordinary clarity. The universe has given us that remarkable gift, not safety, not permanence, but comprehension. We are the cosmos looking at itself, using the tools of mathematics and observation to map its own structure and its own tendencies. We know that mass extinctions have happened. We know with high confidence that they will happen again. We know the categories of mechanisms that drive them. We know our timescales of vulnerability. And that knowledge, sobering as it is the beginning of something rather than the end. A species that understands its vulnerabilities has options that a species without that understanding simply does not have. The physics of planetary defense, still in its early stages, is real. The physics of self-sustaining habitats in space, still largely theoretical but grounded in sound principles, is real. The idea that the long-term persistence of life may require it to expand beyond a single planet is not science fiction. It is a straightforward conclusion drawn from the same geological and astronomical data we have been examining. Consider the analogy of a species confined to a single island. If a volcanic eruption destroys that island, the species is gone. But if some members of the species have spread to neighboring islands, the lineage continues. The expansion does not prevent the eruption. It simply changes what the eruption means for the continuation of the story. On a cosmic scale, the island is this planet, and the ocean is the solar system and beyond. The mathematics of long-term survival, when applied to complex life and the range of extinction mechanisms we have identified, points toward the same conclusion again and again. Resilience requires distribution. A single node in any network is a catastrophic vulnerability. Life, if it is to persist on timescales comparable to the one over which it has existed on this planet, cannot afford to remain confined to a single point in space. There is something that feels philosophically significant about this conclusion, though not in a way that softens the underlying physics. The universe operates by laws that include the seeds of destruction for any particular configuration of matter, no matter how complex or how marvelous. Stars explode, climates shift, orbits are perturbed, volcanoes erupt. These are not anomalies. They are the normal operation of a universe governed by thermodynamics, gravity, and nuclear physics. Life, wherever it exists, must navigate these forces or be swept away by them. What makes this moment in the history of this planet unusual is not that life is threatened. Life has always been threatened. What makes it unusual is that a form of life has emerged that can perceive the threat, characterize it with mathematical precision, and at least in principle begin to respond to it on the appropriate scale. Whether that response will ultimately be sufficient is a question the physics alone cannot answer. It depends on choices, on resources, on the degree to which the awareness that drives the science translates into the sustained effort that a challenge of this magnitude requires. But the first step is always the clearest picture of what we are actually dealing with. And what we are dealing with is this. We live on a geologically active planet, orbiting a brightening star in a solar system that moves through a galaxy whose gravitational environment periodically perturbs the debris left over from our own formation. The history of this planet is written in rock layers that record over and over again the consequence of forces operating at scales we did not create and cannot eliminate. The next chapter of that history has not been written yet, but the forces that will write it are already in motion, governed by laws that have not changed since the first moments of time and will not change when we are gone.